Hello, Bea here, and welcome back to Integrated Physics and Chemistry. I want you to take a look at this table of shapes to see if you can recognize a pattern. Once you see the pattern, I want you to try and figure out which shape is missing in box A and which shape is missing in box B. Here is the completed table. How did you do? This process of placing things in a table in a specific order and then using this order to determine missing pieces is exactly what Dmitri Mendeleev did in 1869 when he designed the periodic table of the elements. Mendeleev set out to organize the elements in a way that made the information easy to understand. He noticed that when he put the elements in order of increasing atomic mass, they would naturally form columns of elements with similar properties. In fact, he even knew where to leave blanks for yet-to-be-discovered elements, and was able to accurately predict the properties of those missing elements. But before we get started, let's look at our goals for this lesson. By the end, you'll be able to explain how the chemical elements are arranged on the periodic table. Identify the important groups of elements on the periodic table. Explain the main properties of metals, nonmetals, and metalloids. Dmitri Mendeleev's periodic table arranged the elements by increasing atomic mass, and it was so close to being correct. In fact, there were only a couple of known elements that didn't fit the trend. In order for their properties to align in the correct column, tellurium had to come before iodine, even though its mass was slightly larger. Because of these exceptions, in 1913, Henry Moseley changed the periodic table to an organization based on atomic number instead of atomic mass, and it became the periodic table we use today. The periodic table can tell us so much about the elements and their properties. Once Moseley finalized his periodic table, where the elements were arranged by increasing atomic number, he found that within the column there is a pattern in the physical and chemical properties of the elements. This is called periodic law, or periodicity. As we have learned so far in this lesson, the periodic table is organized in a very intentional way. If you look closely at this periodic table, you will notice that each box has the element's name and a symbol. The chemical symbol for an element is very important and is usually used more than its name. Think of the symbol as a nickname and the element's name as its formal first name. Scientists tend to use the symbol whenever possible. What do you notice about all of the symbols in this periodic table? There are two types of element symbols, either one letter or two letters. If the symbol is only one letter, that letter must be capitalized, like the N in nitrogen. If the symbol is made of two letters, the first letter must be capitalized and the second letter must be lowercase, like the capitalized F and lowercase e in the symbol for iron. You might be wondering why some of the symbols don't seem to match the name for the element. That is because the symbols are based on the Latin name for the element. Iron in Latin is ferrum, so the symbol Fe comes from there. When looking at a periodic table, you can clearly see the columns and rows into which the elements are organized. However, instead of columns and rows, we use the terms groups and periods. Groups are the vertical columns of elements, and the elements in a group share similar properties. The horizontal rows in the periodic table are called periods. As you move from left to right across a period, the properties of the elements change. There are many different ways that you can break up the periodic table. It's often broken up into metals, nonmetals, and metalloids. As you move from left to right across the periodic table, there is a gradual shift from metallic properties to the properties of nonmetals. Looking carefully at the periodic table, you will notice a section of elements colored pink and labeled metalloids. These elements share properties of both metals and nonmetals and form almost a bridge between the two very different types of elements. Arsenic and antimony are examples of metalloids. Fun fact, antimony was used for mascara and eye makeup in ancient Egypt. To the left of the metalloids, in yellow, are the metals. These elements are solids, except for mercury, which is a liquid metal. They are good conductors of heat and electricity, shiny and malleable. When something is malleable, it can be easily hammered into thin sheets. Gold, for example, is very malleable, which is why it is commonly used for jewelry. To the right of the metalloids in blue are the nonmetals. These elements are usually a gas or a brittle solid, are poor conductors of heat and electricity, and lack luster or shine. Carbon, in the form of graphite, is a brittle solid. If you are writing with a pencil right now, you are taking advantage of that brittleness to write your notes. Another example of a nonmetal is chlorine, which naturally occurs as a yellow gas. As Moseley discovered over 100 years ago, when you organize the elements in order of increasing atomic number, they form columns or groups of similar properties. These groups are numbers 1 to 18 from left to right. Let's take a moment to discuss some of the specific groups on the periodic table. The alkali metals are found in group 1. These metals, lithium, sodium, potassium, rubidium, cesium, and francium, are extremely reactive metals, especially when they come in contact with water. The group 2 metals are called the alkaline earth metals. These metals, beryllium, magnesium, calcium, strontium, barium, and radium, are still highly reactive, but slightly less than the alkali metals. They are also slightly harder solids compared to the alkali metals. The rest of the metals are found in groups 3 to 12 and are called transition metals. These metals are harder solids and tend to be the elements you think of when you hear the word metal. Gold, silver, copper, and iron, for example. While the elements in groups 13 to 16 are important as a group, they don't have many defining characteristics. So we are going to jump over to group 17, the halogens. These nonmetals are very reactive. So much so that they can't exist as single atoms in nature. These elements are either part of a larger compound with other elements or bond with another atom of the same element to form diatomic molecules. Di means two, so diatomic means two atoms. The last group we're going to discuss is group 18, the noble gases. The noble gases are colorless and odorless and completely non-reactive. I think of them as the nobility of the periodic table. They don't need to interact or react with the commoners or the rest of the periodic table. As we went through the lesson today, we discussed how the periodic table is organized and the properties of major categories and groups of elements in the periodic table. Our next lesson is a review and assessment of what you have learned during our atoms, elements, and the periodic table unit. Until next time, remember that the universe is vast and full of surprises, so never stop exploring.
Hey, hey!